is an extension of the fundamental theorem of calculus. So we can think of Green's theorem as a two-dimensional version of the Green's theorem as a two-dimensional version of the fundamental theorem of calculus. Now I want to share my computer screen. Okay, can you see this computer screen I'm sharing with you?
Yes, Doctor.
Okay, thank you. Okay, I've uploaded the lecture material we discussed yesterday into the e-learning. Yeah, and we have looked at several applications of Green's theorem and also the Green theorem formula here. So this is the statements of Green's theorem. Now, next I want to discuss what is called the Stokes theorem. The Stokes theorem is a three-dimensional version of the Green's theorem. You see? See, Green's theorem relates the double integral over a region, omega, with a line integral over its boundary, right? Over its boundary here. So now we want to look at the extension of this Green's theorem to three-dimensional space, where now it involves, instead of a plane region, we now have a surface. Okay, instead of a two-dimensional plane region, we now have a surface region, and how it relates to the boundary of a surface. Yeah, that is the essence of Stokes theorem, you know. But the Stokes theorem involve many concepts, you know. Let me show you what is Stokes theorem. Yeah, this is the statement of Stokes theorem. This if Green's theorem involves two-dimensional region with its boundary, then Stokes theorem involves three-dimensional surface with its boundary. So Stokes theorem is a three-dimensional version of Green's theorem. Yeah. Okay, let's suppose we have a surface sigma here in a 3D space. Okay, this is a surface. Suppose a sigma, capital sigma, is an oriented surface with normal vector n. Okay, and a finite surface area. And assume the surface omega is bounded by a curve C, as shown here. Yeah, with its orientation induced by gamma, by the surface gamma. I will explain to you this orientation. Suppose F is a vector field that is defined and continuous on the surface sigma here. Remember, a vector field assigns a vector to a point, right? To a point. So here it is a three-dimensional vector field. So the point is x, y, z. And assume the components of the vector field F have a continuous partial derivatives at each point sigma, yeah, not on the curve C. Yeah. Here is the Stokes theorem. There's a line integral here. Remember the integral on the left is a line integral. Okay, we have solved this line integral using parametrization method. Also by using this the Green's theorem. Yeah. uh, and also what? If it is two-dimensional, we can also solve this line integral using what? Using Green's theorem. If we have also seen the use of the fundamental theorem of line integral, yeah, for evaluation of this line integral. Now, according to Stokes' theorem, this line integral is also equal to the double integral on the surface. Okay, this line integral on the left is a three-dimensional, where C is a space, is a curve in space. Yeah, yeah, and it is equal, according to Stokes' theorem, this line integral in three-dimensional space is equal to the surface integral of the curl of the vector field F dot with the normal vector n, and this is d capital S. Yeah, d capital S. It is not ds. Last time we used d small s, right? For surface. I mean for arc length. Yeah, for arc length measure. Now this is a surface measure. Okay, so this double integral on the right is on the surface. Yeah. It is called a flux integral. It is a special type of surface integral. Yeah. So there are many things that I need to explain before we can discuss Stokes' theorem, yeah, the three-dimensional version of the Green's theorem. You see, this Stokes' theorem relates the surface integral with respect to a line integral on its boundary. Yeah. So in order to understand this Stokes theorem, what we need to understand, we need to understand the surface integral, and we need to understand flux integral. Okay? Yeah. We need to understand the surface integral as well as the flux integral. Yeah. So, so I cannot discuss this Stokes theorem right away. There are uh, some basics of Stokes theorems that I need to discuss first. Yeah, the idea of surface integral and the flux integral. That's what I want to discuss next. The idea of surface integrals. Okay. Before we can discuss surface integral, let's first look at the the double integral formula for finding the surface area, okay, of a surface. Yeah. Okay, we know that z equal to fxy. The graph is some surface, right, in a three-dimensional space. Okay, suppose the domain is bounded, is restricted to this region R. Right? Suppose the xy here is restricted to this region R on the xy plane. So for each xy on this region R, there is a point z on the surface. Okay. Yeah. So we can say that the region R is the projection of the surface on the xy plane. Okay. If you shine a torchlight from above the surface, it will create a shadow here, R on the xy plane. So R is the domain, yeah, of the domain of the function z equal to fxy. Okay, so the surface area of surface sigma here is equal to the double integral over the region R, the square root of f partial x squared plus f partial y squared plus 1 dA. Yeah, and dA. This is the area element. It could be dx dy or dy dx. Yeah. We can prove this using the same approach that I have shown you several times. You know, We use what? We partition the surface into smaller subsurface, and then we use an estimate. So using that same idea, okay, uh, we can derive this formula. This formula can be derived. Okay. So ds, you see, this is capital S. This is not small s. This is capital S. So ds is equal to the square root of f partial x squared plus f partial y squared plus 1 dA. Okay, so this is the surface area element here. D capital S is the surface area element. Okay, now we look at this idea of a surface integral. I want to introduce to you this idea of surface integral through a problem of finding a mass of a say of a very thin sheet of metal in the form of a surface here. So let sigma denotes a surface of very thin sheet of metal. Yeah. For two-dimensional, we discuss lamina, isn't it? A thin sheet of metal on a two-dimensional sheet, a thin sheet of metal, we call it a lamina. So now we consider sigma as a surface of a very thin sheet of metal. Yeah. And suppose it is of varying density. The density on the surface varies from point to point. So the density function is gxyz. It's called the mass density or mass per unit area of sigma at the point xyz. So what is the mass? What is the mass of the total sheet here? Or metal sigma here. So we use the same approach that I have shown you several times. We partition. In this case, we partition the surface into small partitions, right? And suppose it is divided into n partitions, and let's consider this small partition here, which denoted as sigma k. Okay, and there are many points on the surface sigma k. So let's choose a representative point x k, y k, z k, and this surface sub k. If we there's a projection on the xy plane in blue here, which I call it RK. Yeah. So we come up with an estimate first. What is the mass of the surface sigma k? It is equal to the density times the surface area. Okay. This is approximately equal to the density at the representative point xk, yk, zk times the surface area of sigma k, denoted here as delta sk. See, this S is capital S, yeah? Yeah. So to come up with a better and better estimate, we use, so the total mass of the surface sigma is approximately equal to the sum of the approximation of each mass of sigma k run from 1 to n, okay? Suppose we partition the surface into n partitions, right? So we determine the approximation of each mass of the partitions. So the total mass of sigma is approximately equal to the sum of the approximated mass of the partition sigma k. Yeah. So to come up with a better and better estimate, we use smaller and smaller partitions. So that means increasing the number of partitions n here. So we define the actual mass as the limit of this summation as n tends to infinity. Yeah? So as n tends to infinity, of course, the partition of the surface sigma k gets smaller and smaller. So this the surface area of the partitions tends to 0. All right. So if it exists, then we define the mass of the surface sigma equal to this double integral over the surface sigma d capital S. Okay. D capital S, the surface area element here. Yeah. So this is a surface integral. Yeah. This double integral is over a surface. Yeah. It's not over a region on the xy plane. Okay, it is a double integral here. It is over a surface, so that's why we use the area element here, d capital S. Yeah, yeah. So how do we evaluate this surface integral here? So if the surface has the representation z equal to fxy, okay. So suppose z equal to fxy is the equation of a surface sigma, then okay, this surface integral uh, gxyz d capital S over the surface sigma is equal to, so we replace this z here by fxy, and remember d capital S is equal to the square root of f partial x squared plus f partial y squared plus 1 dA. So this is double integral over the region R on the xy plane. So it comes back to the evaluation of double integral that we have seen before, that we have discussed, many times before. So this is how we calculate surface integral. Yeah? So the Stokes theorem is related to this surface integral. So we need to understand how to first evaluate surface integrals before we look at Stokes theorem. Okay, so let's look at some examples of evaluation of surface integrals. Okay, as an example, suppose we want to evaluate suppose let sigma be a, a part of a cone, be the part of the cone z equal to square root of x squared plus y squared over the region x squared plus y squared greater than or equal to 1, less than or equal to 4. Okay, with density, with density function given by g was all delta delta x y z equal to z squared. Okay, determine the mass of the surface sigma. Yeah. We should add here, let the surface sigma be a part of the cone z equal to square root of x squared plus y squared over the region x squared plus y squared greater than equal to 1 less than equal to 4 with density function delta equal to xyz z squared. Determine the mass of the surface. So we know that from our previous discussion, the mass is equal to the double integral over the surface integral over sigma, and then we have what, the density function gxyz d capital S. Density function, yeah, in the yeah, in the in the in our discussion here, we use g to represent mass density. Yeah. So the total mass is equal to this surface integral over the surface sigma of g. Okay? G here is the density function. ds, d capital S. Okay. Now d capital S is equal to sigma squared here, and I mean z squared. All right. So how to evaluate this surface integral? So let us first make the sketch of the surface. Okay. Let's make a sketch of this surface here. This is a cone, right? So it is some cone, and you should know what is the shape of the cone by now. All right. So this is the cone. Uh, z equal to the square root of z equal to the square root x squared plus y squared here. Yeah. But it is not, this is infinite cone, isn't it? It's unbounded. But here it is stated, this finite cone is restricted to x squared plus y squared greater than 1, less than or equal to 4. So we know that x squared plus y squared equal to 1 is a circle, right? It is a circle. It is a circle of center, say, of 1. All right, so this blue circle on the xy plane has the equation x squared plus y squared equal to 1. And then we have another circle of bigger radius, 2. 4 is equal to 2 squared. So let's draw a bigger circle. Right, like this. Doesn't have to be very accurate. So this bigger circle has the equation x squared plus y squared equal to 4. So it is a circle centered at 0 of radius 2. Yeah. So this is R actually, right? This blue region is actually R. All right. So it is a part of the cone with xy in this circle here. This in this circle. So it has this shape actually. Yeah. So this is sigma, the surface sigma. This part of the cone, uh, that part of the cone that's over the region R here. Okay, that is the sigma. So, and suppose the density of this surface sigma is equal to z squared. So what is the mass? What is the mass? So it is equal to, so here this is the surface z equal to fxy. Okay, that is the surface z equal to fxy. So remember the formula just now, the technique for evaluation of the surface integral. Yeah, this is the technique here. And, okay, let me paste it here. So make it smaller. Yeah. Okay, so we recall this. We recall this formula to evaluate the the surface integral here. So g is z squared here in this case. G here is equal to z squared, and z, and we have fxy here in this formula. So fxy comes from the surface. The is the equation of the surface. Yeah. So zxy is the equation of the surface. Z equal to square root of x squared plus y squared. So this is fxy, the equation of the surface. And so therefore, the mass is equal to the double integral over the region R. Okay, R is that circular ring, yeah, on the xy plane. So we have z, we need to replace z by fxy. First, we need to replace z by fxy squared, and then f partial x squared plus f partial y squared plus 1 dA, okay, according to the technique here. Yeah. Uh, what is fxy? Yeah, fxy is the square root of x squared plus y squared. So the square of f is the same as x squared plus y squared. So what is f partial x? We also need to calculate f partial x. It is what? Use the chain rule. It's the same as x over square root of x squared plus y squared. And f partial y is equal to y divided by the square root of x squared plus y squared. You see, you need um, to be able, to take partial derivatives correctly here. Then you need to be able to calculate this double integral correctly. If you did not manage to get the partial derivatives f correctly, then of course you will get a wrong integrand for the double integral. So maybe things will become too complicated for you to solve. Yeah. So we want the square of f partial x. So that means it is equal to x squared over x squared plus y squared, and f partial y squared is also is y squared over x squared plus y squared dA, right? dA. But this is the same as 1, isn't it? This this whole thing is equal to 1 actually, right? If you write this two fraction as a single fraction, then you have x squared plus y squared divided by x squared plus y squared. Okay, now it remains to determine, so this is equal to the double integral over the region R of x squared plus y squared dA. Look at the region R. It is circular, isn't it? This region R here is bounded by two circles. So that suggests using polar coordinates, right? That suggests using the polar coordinates. Yeah. So the region R, uh, observe that the region R is r theta, where r is between the smaller radius 1 and less than equal to the bigger radius 2. And theta is between 0 up to 2 pi, because this is a full circle. Yeah. Okay? And therefore, and we know x squared plus y squared equal to r squared in polar coordinates. So we have a double integral of r squared, and the area dA element is r dr d theta. Okay? So we are using the order dr d theta here, where r is between 1 and 2, and theta is between 0 up to 2 pi. Okay? So I can evaluate this double integral as a product of two integrals, because the limits are all numbers, and the integrand is a product of a function of r times a function of theta, which is a constant. So I can write this as the integral 0 to pi 1 d theta, then the integral from 1 up to 2 r cubed dr. Okay, first y. Second integral is r to the power of 4 over 4, right? So this is 2 pi r to the power of 4, where r is from 1 up to 2. So this is the same as 2 over 4 is 1 half, so we have pi over 2. Next, we replace the limit, r equal to 2, and then r equal to 1. So this is pi over 2, 16 minus 1, which is 5, 15 over 2 pi. Okay, unit mass here. All right, is that correct?
Yes, Arthur, correct.
Is it correct?
Yes, Arthur.
I got a different answer because I made a mistake here. I'm sorry, I made a mistake. You see, there's a plus 1 there. That's plus 1 is missing here. Yeah, plus 1 is missing here.
Oh, oh.
So we have square root 2, in fact, not 1, but it is square root 2. Yeah, square root 2. So I need to have square root 2 throughout the remainder of the calculation here. Yeah, so I should have square root 2 here. So we should have square root 2 everywhere here and square root 2 there. Okay. So it is square root 2 over 2 times 15 pi. Yeah. Yeah. So luckily it's just a small mistake here. Ada soalan?
Ada. Okey lagi setakat ni.
Ada ya? Let's look at another example of evaluation of this surface integral. So evaluate this surface integral 2x d capital S, where gamma is the surface x plus y, say plus z equal to 1 in the first octant. In the first octant. Okay, in the first octant. Okay, that's all. So this is nothing to do with mass or density. It's just a exercise. It's just an evaluation of a surface integral. Right? So what is the surface here? Let's make a sketch of the surface. We have x here, y, and z. Okay. So we know that the surface is this has intercept 1, 1, 1 on each axis. So this is the surface. Yeah, sigma. Okay, and it can also be written sigma. You see, from this equation here, we can say that z is equal to 1 minus x minus y. So this is our fxy here. Z is 1 minus x minus y. Yeah. So therefore, this surface integral, you make sure you use capital S here, not small s, because this is related to surface integral. Right, so it is equal to, according to the technique, it is equal to 2x square root of f partial x squared, f partial y squared plus 1 dr. I mean dA. Okay, yeah. So dA. So it is so this surface. This is the region R here. This blue region here. This is the region R. Right? The projection of the surface on the xy plane is that region R there. So what is f partial x, f partial y here? Anybody?
-1.
From this equation, what is f partial x? -1, isn't it? And so is f partial y. It's also -1. Yeah. So we have here -1 squared plus -1 squared plus 1. So it is 3, just a constant 3 here, a square root 3. All right. Yeah. So now, how to evaluate this double integral? What are the bounds for x and y in this region R? If I draw this region R on the vertical xy plane, then it is this shape here. It's a triangular region. Yeah? It's a triangular region. And this line is equal to y plus x equal to 1. Y plus x equal to 1, which means y equal to 1 minus x. So here x is from 0 to 1. Okay, so we know from this diagram that R consists of all points x, y, such that x is between 0 and 1, and y is from 0 up to 1 minus x. Okay, so that means you have to integrate with respect to x first, because y is bounded by a function of, so let me put the 2 up as well. Okay, y is between 0 up to 1 minus x, between 0 up to 1. So we differentiate first with respect to y. We get x, y. Y is from 0 up to 1 minus x and dx. So the replace y by 1 minus x, so we get x times 1 minus x dx. Okay? Yeah. So I leave it to you to show that this is equal to square root 3 over 12. It has the value square root t over 12. Yeah. So this is another example. Here we don't need polar coordinate. Yeah, we can work entirely using the Cartesian coordinate. Okay, let's look at another example. We have seen one example related to a cone, and one example related to this surface. Let's look at another one more example, this time related to a sphere. Evaluate this surface integral 1 plus z d capital S, where sigma is a hemisphere, um, z equal to the square root of 1 minus x squared minus y squared. Okay, so this is just evaluation of a surface integral here, nothing to do with density or mass. Okay, just evaluation. Yeah. So this time the sigma is a surface. Okay, sigma is a upper hemisphere. It is of radius 1, right? Of radius 1. Yeah, this hemisphere of radius 1. So here we have z equal to square root of 1 minus x squared minus y squared. So this is the function fxy now. So according to the technique for the evaluation of the surface integral, what we need to do, we need to replace z by the surface, and then ds becomes what? Square root of f partial x squared, f partial y squared plus 1 dA. Okay, dA. So here fxy is the square root, isn't it? Is the square root of what? 1 minus x squared minus y squared. And what is f partial x here? What is f partial x? Yeah. This fx implies what? Use the chain rule. It's minus x, right? Minus x over the square root of 1 minus x squared minus y squared. And f partial y is minus y divided by the square root of 1 minus x squared minus y squared. So we want the square. What is that equal to? It is equal to x squared. Yeah, it's equal to x squared here divided by 1 minus x squared minus y squared. F partial y squared is y squared over 1 minus x squared minus y squared and plus 1. So this is equal to what? If we write this as a one summation, we get x squared plus y squared plus 1 minus x squared minus y squared. Everything divided by 1 minus x squared minus y squared equal to 1 over 1 minus x squared minus y squared. So that is the square root. So now we want the square root of that. So it is 1 over the square root of 1 minus x squared minus y squared dA. Okay. So we have evaluated f partial x squared plus f partial y squared plus 1 separately. Alright, and then we take the square root and then substitute into the double integral here. Okay. So this can also be written, if I multiply that 1 over square root into the bracket, we will get 1 over the square root of 1 minus x squared minus y squared plus 1 dA. Okay, what is the a good way to evaluate this double integral here? What is the region R? Where is the region R here? Anybody?
In the xy axis.
It is in the circle, isn't it? R
Yes.
is the region inside the circle on the xy plane, right? Yeah, that is the region R here. This is a blue shaded region here. Yeah, this is the region R. So it is circular. Okay, it is circular. So that means we can use polar coordinate again. Yeah, circular. So R consists of all polar coordinates theta. R is between 0 and 1, and theta is between 0 up to 2 pi. Okay, so I can use polar coordinate to evaluate this double integral over the region R. And by in terms of polar coordinate, we have the square root of 1 minus R squared plus 1. dA becomes R, dr, d theta. Okay, so integrate over R is between 0 to 1, and theta is from 0 up to 2 pi. Yeah, I can again write this as a product of two integrals because the limits are numbers, and the integrand is a product of a function of R and a function of theta. Okay, so the first integral is clearly 2 pi. The integral R is from 0 up to 1. Yeah. Okay, how to evaluate this integral with respect to R? Okay, let's calculate it separately. R over dr is equal, you can write this as a two integral, isn't it? The integral R over square root of 1 minus R squared dr plus the integral 0 to 1 of R dr. Yes. Okay. You can evaluate the first integral by substitution. Okay, you can use the substitution u equal to 1 minus R squared. Therefore, du is minus 2R dr. And the second integral here is half R squared, 0 up to 1, which is 1 half. So I leave it to you to complete the calculation. Show that the final answer is equal to 3 pi here. It's equal to 3 pi. Yeah? I leave it to you to complete the calculation. Yeah. So this is another example of an evaluation of a surface integral here. Okay, let's go back to the Stokes theorem once more. Okay, this is Stokes theorem. So you see, the integral on the right here is a surface integral. It is a double integral over the surface sigma, and it is ds, d capital S. Yeah. So the integral on the right here is actually a surface integral. But the integrand has a different form. It is a curl of a vector field f dot with a normal vector n. Okay, this is something that I need to explain. Why? It is also called a flux integral. So it's also the surface integral on the right here is also called a flux integral. So it is a special type of surface integral. This is what I need to explain next. The idea of a flux integral. Yeah. So this we have a vector field f here in the surface integral, and we have a normal vector n here in the surface integral. So I need to explain this, the idea of the flux integral here. Okay. Why in the Stokes theorem we have the surface integral with integrand of this form here. So again, it relates to a surface, okay, sigma, and the boundary of the surface is C here. Okay, is some curve C, and there's a normal vector here of the surface. Yeah. And this curve C has an orientation. Okay? Sigma, the surface sigma is bounded by a curve C, which orientation induced by the surface. So all this needs an explanation. So let's go to the now I discuss the surface orientation. Yeah, in the Stokes theorem requires a surface orientation here. So consider a surface sigma with two sides. Okay, a sigma is a surface in 3D, and of course it has the outer side and the inner side, right? Yeah. This is the exterior of the surface is called the outer side. The interior of the surface is called the inner side. Yeah. So a surface sigma has two sides, the exterior surface as well as the interior surface. So banyak macam satu contoh kita punya songkok lah kan, ada bahagian luar, ada bahagian dalam kan. Permukaan luar, ada permukaan dalam, macam tu lah kita punya topi ke, kita punya cap ke kan. Apa macam ada bahagian luar, ada bahagian dalam kan. Kita
Betul,
punya
sir.
baju, kita punya baju pun ada yang bahagian luar, ada bahagian dalam kan. Kita punya baju pun can be considered as a surface. Yeah. Okay, so suppose the surface has this representation by the equation z equal to fxy. Yeah? So two unit normal vectors exist for a surface, one pointing outward of the surface and the other pointing inward. Okay, given a point on the surface, then there are two possible normal vectors. Yeah? One either pointing outward of the surface or pointing inward. Yeah, pointing inward. Yeah. So we discussed normal vector, tangent vector before this, right? We have tangent vector, normal vector. Yeah. So the normal vector is orthogonal to the tangential vector. And the normal vectors that point outward is equal to minus f partial xi. This is related to gradient. Yeah, the idea, this formula is derived using the concept of gradient actually. Yeah, but I do not want to go much into detail. Yeah. So let's just uh, look at the formula here. The two unit normal vectors n that can be chosen is the outward normal or upward or the downward normal. Yeah. So like this one is outward in the upward direction and this one is in the downward direction here. Yeah. So it is if in the upward direction the vector normal n is equal, it's a vector, right? So we have so it is in the form of a vector. So we have vectors I, j, k as well. Okay, and the one below is the normal vector in the downward direction. So you can see they are negative of each other, right? The normal vector in the upward direction is the negative of the normal vector in the downward direction. So we need to know this when we want to discuss Stokes theorem. We need to know this ideas of normal vectors to a surface. Because if you look at the statement of the Stokes theorem once more, we have this n, right? We have this n in the formula here. of the surface integral. This is dot n. So this n refers to a normal vector. Yeah. So a normal vector here is said to be in the where is it? It's orientation induced by sigma. Yeah, in orientation induced by sigma, a normal vector n here. Suppose sigma is an oriented surface with normal surface, normal vector n and finite surface area. Why is a surface also oriented? Uh, we know a curve has an orientation, isn't it? A curve can have an orientation. But how is it sigma has an orientation also? Uh, so that also the thing that we need to understand. This orientation of a surface, yeah, surface orientation here. Yeah. Suppose a sigma, we have a surface sigma has a curve C at its boundary here. Yeah. So if the surface is finite, of course it has a it has a boundary. Uh, the orientation of the surface sigma induces an orientation of the curve C. See, there is a right hand rule here. It follows a right hand rule here. Yeah. In the if the normal vector is upward, right? See, the thumb is in the outward direction. See, the remaining four fingers, you see, induce the orientation for the curve C. So we call this the right hand rule. Yeah? We use the right hand rule here. So the orientation of the surface sigma induces an orientation of the curve C. So if the thumb here, right, is in the outward direction of the surface sigma, so that induce the orientation of the boundary C here. Okay, it's called the right hand rule. So that is uh, the idea used in the Stokes theorem. Sigma is an oriented surface with normal n and finite surface area. Assume sigma is bounded by a curve C with its orientation induced by the sigma. Okay, so here following the right hand rule, we have a surface sigma here. Following the right hand rule, it is the outward normal, right? Outward normal. So by the right hand rule, the boundary of the surface sigma is according to this orientation here. Yeah. Okay. Okay. Now we understand now the orientation of the surface sigma. We understand now the normal vector n. Okay, for the surface sigma. So we know this is the This is the what? The surface integral here. But we also have this curl f here coming in. Okay, this is a flux integral actually. Such a surface integral of this form is also called a flux integral. And it has application. In fluid mechanics, a flux integral has an application. So this is what I want to discuss with you. Yeah, it is okay. Yeah. In fluid mechanics, there's a flux integral, okay, may arise from this study of fluid mechanics. So let's consider the problem of finding the rate of fluid passing through a surface in the direction of the vector normal n. So first, consider the simple case first, where sigma is in this vertical direction. It's a flat surface. Yeah. Suppose sigma here is a flat surface, and water or fluid is coming. Yeah, is flowing across it through the surface. Okay, fluid passing through a surface. So this is the vector in the same direction of the vector n. So we have a surface sigma, and suppose this is the normal vector here. Okay, we consider this direction as the normal vector n here. And suppose fluid is flowing in the same direction as the normal vector n. Okay, the normal vector is perpendicular to the surface sigma here. Okay, suppose this is at the time t, right? And at this a time t plus h. Okay, as varies as the time varies from t up to t plus h. So a certain amount of fluid has already passed through, isn't it? Passed through the surface. It is equal to, what is the amount of fluid that has passes through the surface? Okay, n is the vector normal to the surface sigma. Capital S is the surface area of sigma. Rho is the fluid density. And vector v here is the fluid velocity. Yeah. So the amount of fluid that has passes through the surface sigma is the speed times the speed of the fluid times h, time. Okay, speed times time. The time interval here is h. From t up to t plus h, the time interval is h, right? Yeah, so the volume of fluid passing through sigma from time t to time t plus h is then h times the speed. Okay, the modulus of the velocity gives us the speed times the surface area. Surface area of sigma. So we have like a cylindrical object right here. It looks like a cylindrical object. The height is the speed time h, and then the surface. Okay, so the volume is the surface. The area of is this area of the surface sigma times the height, times the length here. So that gives us the volume. So the mass of fluid during the time interval t to t plus h, if it is, if rho is the what, the fluid density. Okay, so the mass of fluid is density times volume, isn't it? Density times volume gives you the mass. Yeah, so density here is described by rho. So the rate of fluid passing through sigma in the direction of the vector normal n with respect to time is, what is the rate of fluid? Is the mass of fluid divided by time. Yeah, the rate of fluid passing through sigma in the direction of is with respect to time is, you take there's a limit, right? The limit, yeah. You take the limit, just, yeah, which is the what, the mass divided by time here. So h cancel out. Yeah, yeah, h cancel out. So it is equal to rho, the density times the speed times the surface area. This is for the simple case. For case 1 here, it is simple. Rho is a constant. The sigma is just a flat surface here. Okay. Now we consider the second case. Case 2 here. Okay, now case 2 is not as simple as the case 1 anymore. Now suppose it is no longer the fluid is no longer in the same direction as the vector n, as the normal vector n. All right. So what is the amount of fluid that has passes through the surface? Here we use what is called the angle here. Suppose this line here makes an angle theta. So there's a, you see a velocity, we have a component, yeah, component along theta here. So this is of length. The length here is now the modulus, the speed v times h times cos theta, where theta is the angle here of the direction of the normal vector here of the surface. So from the previous idea, to find the rate of fluid passing through sigma in the direction of n, we use the same formula as above, but now we have just a multiplication with cosine theta now. Okay, again h cancel out, so we have rho times the modulus of speed v cos theta times capital S. Capital S, the surface area. Now the modulus of the velocity v times cos theta is actually v dot n, right? The velocity vector v times the normal vector. Because the normal vector is always a unit vector here. And v, you see, the angle between the velocity v and the normal vector n is also theta. So the rate of fluid passing through sigma in the direction of the normal vector n can be written as a dot product here. Rho, okay, rho is the density times velocity vector dot product with the normal vector times the surface area S here. Okay, now we move on to a more challenging case, where now the surface, sigma, okay, is any surface on the uh, uh, in three-dimensional space here. And suppose we have a fluid, passing through this surface. You see, the surface sigma is no longer flat. It may take a curve form, right? So what is the rate of mass fluid passing through sigma in the direction of the vector n? So again, we use the idea of partition, we use the idea of partition, divide the surface into smaller partitions, and then approximate. Okay, use the approximation. It can be shown that it leads to this surface integral over the surface sigma, rho is the density function, times the velocity vector v dot with the normal vector. So here we have varying normal vector here, right? Point to point. You see, on the surface, we have normal vector that varies from point to point. Yeah, from point to point, it varies. Yeah. So this integral, this kind of surface integral, is called the flux integral. This is the flux integral that we have in Stokes' theorem. So now I've introduced you the concept of flux integral using through a problem in fluid mechanics. Yeah, finding the rate of mass. Yeah. Okay. So this is a surface integral actually, but the integrand has this form, rho times vector v dot the normal vector n. So this kind of surface integral is also called the flux integral. Now, how do we evaluate a flux integral now? Okay, how to evaluate this flux integral? Because in Stokes' theorem, the surface integral in the Stokes' theorem is actually a flux integral. Okay, in Stokes' theorem, the surface integral that we have in Stokes' theorem is actually a flux integral here. This is a curl of a vector field F. It's a vector, right? The curl of a vector field F is a vector. Yeah. So how to evaluate this flux integral? So we go back to the here. Okay, here explains how to evaluate flux integral. So generally, a flux integral is an integral of the form capital field F dot n. Okay, so now I'm going to replace this rho times vector field F as a capital F. Yeah, more generally. Yeah. So more generally, a flux integral has this form. The surface integral over a surface sigma times vector field F, yeah, dot n. Yeah. So this vector field F could be the velocity field, it could be an electric field, could be a gravitational field. Yeah. And let the surface sigma be represented by z equal to fxy. And let capital F, the vector field F, be represented in terms of its component. M vector I plus N vector J plus P vector K. And suppose N points upward, in the upward direction. Then we replace this in the flux integral. We replace capital F, the vector field F, by its component. Okay. And then remember the normal vector in the that points upward has this ratio here, has this form. I showed you already, isn't it? The normal vector, the formula of a normal vector that points upward is in this form. Remember? Where is it? Not here. Where is it? Is it here? Where did I discuss that? Here. Okay. This is a normal vector in the upward direction, and the one below is a normal vector in the downward direction. So I'm using these formulas for the normal vector in the evaluation of the flux integral. Where is it? Just now, Stokes' theorem. Yeah. Okay. We replace this normal vector n. If the vector normal n points upward, then we replace this vector normal n by this ratio here. And remember, the surface element ds is equal to the square root of f partial x squared plus f partial y squared plus 1. So it cancel out, right? It cancel out. The square root cancel out. And then we have a dot product of these two vectors. So you know how to take a dot product of two vectors, right? You multiply the components by component, and then we add them up. So we have m times minus f partial x, so we get minus m f partial x. Next, we multiply n with minus f partial y, so we get minus n f partial y. And lastly, we multiply p with 1 here, so we get p. Okay, so it reduces to a double integral. So the flux integral reduces to a double integral over a region R. Okay, over this region R is the what? Is the projection of the surface on the xy plane. So this is how we evaluate the flux integral, and this is how we evaluate the flux integral in Stokes theorem here. Yeah. And if n points downwards, okay, if n points downward, then we use the other director, what the other normal vector. Then we use the normal vector that points downward. It is this form here. Okay, it is negative. The vector normal n that points downward is negative of the vector normal n's that points upward. Yeah. So here we have minus minus plus, so it now become plus plus minus. So again, the square root symbol here cancel out. So take the dot product. So the result is f partial x plus n f partial y minus p. Okay, what is R? R is the projection of the surface z equal to fxy onto the xy plane. Okay, so so now we can fully understand Stokes' theorem here. Suppose omega is an oriented surface with normal n and finite surface area. Okay, we understand that already. And suppose omega is bounded by a curve C, which is orientation induced by sigma. Okay, we understand that also now. And suppose F is a field vector. So it's a vector field that is defined and continuous on sigma. Okay, and assume the components of the vector field F have continuous partial derivatives at each point of sigma, not on the curve C. Yeah. So here is the result called Stokes' theorem. Then the line integral of the vector field F is equal to the surface integral, okay, of a curl of the vector field F dot the normal vector d capital S, okay, over the surface sigma. Yeah. If F takes this form with components M, N, and P, then we know that the line integral can also be written in this alternative form. So this line integral in the alternative form is also equal to the surface integral of curl F dot n normal vector n ds over sigma. Okay, so there is a proof. There is a proof to this result. I'm going to skip the proof here. Okay. In mathematics, if I teach mathematics student, then I will describe the proof to you, to the students. Yeah. But for the engineering students, let me just let's just apply this result here. Okay, let's compare this Stokes theorem with Green's theorem. As I said just now, if Green's theorem involves two-dimensional region with its boundary, then Stokes theorem involves three-dimensional surface with its boundary. So Stokes theorem is a three-dimensional version of Green's theorem. Okay, I've been talking so much now. Do you have any question? Maybe you have time to look for one example of application of Stokes theorem.
Will the Stokes theorem will come out in the exam?
Yes, yes.
Oh,
Yes, it will be.
it seems hard.
I have taken a lot of trouble explaining it to you, so it certainly is in the final exam.
Okay, doctor.
If you look at our course information, there is a topic on what on Stokes theorem. Where is it? The course information. Yeah. if you look at this, our lecture schedule, see the Stokes theorem here. And that's not all. That's not the end of it. We have another theorem called Gauss divergence theorem, which I will discuss this next week. Yeah, this Gauss divergence theorem. So this will be in the final exam. I think I have shown you some samples, isn't it, of final exam, right? Did I not give you some samples? This is one sample that I've uploaded in the e-learning. There, where is it? Where is it? There's a one question on Green's theorem. Okay. Here, question number 5. You see, we have you see 5a. This is a surface integral here. This is surface integral. Here, the surface is described by sigma, represented by sigma. And then the part B is part C is Stokes theorem. Stokes theorem. The evaluation of this line integral using Stokes theorem, and the surface is described here. It's a triangular closed curve on the plane with vertices. Yeah. Okay. So certainly there will be a question on Stokes theorem on the also here the evaluation of surface integral. Yeah. And here part B is the Gauss theorem. Gauss theorem. Here we have divergence, right? F dot n is divergence. Yeah, we have divergence, and then D capital S also. For Stokes theorem, we have curl F dot n. For Gauss, we have divergence. Yeah, it is actually a triple integral here. Okay.
Okay, thank you, Doctor.
Okay, let's see one example of Stokes theorem before we stop. So this is a sample final exam. Use Stokes theorem to evaluate this this line integral. Okay, here C is a closed curve. Okay, that's why we have this symbol like a circle in the middle of the integral. It means the curve C is closed and in the counterclockwise direction. If the vector field f x y z is equal to 2x minus yzi minus y squared z cube j minus y cube z squared k, and C is the curve uh, around the plane. It's the curve around the plane or encircling. Yeah, maybe the word is the curve of the boundary of the plane. Is where C is the curve. Yeah, around the plane x plus y plus z equal to 1 in the first octant, with orientation, with counterclockwise orientation, with a counterclockwise orientation, when viewed from above. Okay, when viewed from above. So let's discuss sketch first, the surface as described in this problem here. So we have a plane. We know that this is the plane. You know how to sketch, right? There is a plane, equation of a plane. So it has intercept at 1. Yeah, I think we have done similar sketch before. So this is the plane in the first octant. And the curve C, the boundary, right? It has the boundary. So this is the boundary. The boundary of the plane, of the curve, is this red curve here. And when viewed from above, it is in the counterclockwise direction. So it has this direction. So this is the curve C, and the surface sigma is here. It's the surface sigma. Which can also be written as z equal to 1 minus x minus y. So this is our fxy. Yeah. So how to evaluate this integral, this line integral? Okay, if we use the old method, I mean the parametrization method, it will require splitting this integral into into 3 over C1 plus the integral over the line C2 and C3, isn't it? Yeah. So this is like C1, C2, C3. So C is like C1 plus C2 plus C3. Yeah, this is the old method. Okay, the old method. If I want to use the old method, this is what we need to do, the parametrization. So we need to parameterize the boundaries C1, C2, and C3. Okay, yeah, and then we use old method with parametrization method with parametrization. So that's a lot of work, isn't it? That's a lot of work. Yeah. Why it disappear? Why the dot appear? Okay. Okay. So one way is to use the Stokes theorem. Yeah, by Stokes theorem, this integral here is equal to the surface integral over the surface sigma the curl. Curl is also represented by del cross f. Del cross f. ds. Okay. Here we have a normal vector, right? The normal vector is according to the orientation using the right hand rule. It is in the outward direction here. Okay. Using the right hand rule. Okay, we know that n here is in the upward direction. Okay, using the right hand rule. The upward direction. Yeah. So we need to calculate the before we can evaluate this the surface integral. We need to first calculate the curl. Remember how to evaluate the curl of a vector field? We using determinants. Can use the 3 by 3 determinant. And here we have M and P. Right. So what is M and P? M and P comes from here. This is M, this is N, and that is P. Okay? From the components of the vector field F. So let's substitute it here. I'm sorry, this should be partial Z, yeah? Partial Z. So M here is 2x minus yz. P is what? N is minus y squared z cubed. And what? And Q, what is Q? What is P? P is minus y cubed z squared. Okay. I notice that the time is now 12:40. Do you want me to continue, or do you want to stop here and then I'll complete the rest of the calculation and then upload in the e-learning? What do you want to do? What's your preference? Do you want me to continue, or you want me to stop here and then I complete the calculation and then upload this into the e-learning? You said you have a test, right?
Yes, but that's
Are you still with me? Are you
yeah, I
somewhere
think
else?
okay. I think we can take a look after you finish the question.
Okay. All right. Okay, then we stop now. Okay. I'll stop here. I will complete the calculation here. And then I will upload into the e-learning. So next week, we'll go through the calculation quickly. Okay. All right.
Okay, doctor.
Okay. So good luck in your test. Yeah.
Thank you.
Okay.
Thank you,
Thank you,
doctor.
doctor.
So before we stop, we what? Let me show you your QR code for attendance. Yeah.
Doktor,
Yes.
doktor ada record ke kalau yang sepanjang kelas doktor?
Saya tak record lah. Kenapa?
Saya ada record tapi macam ada lah 2-3 kelas yang saya tak datang. Ingat kan doktor ada record saya.
Saya tak record lah. Saya expect student hadir lah. And yeah, and saya tak nak jadi dia terlalu mudah lah untuk pelajar. Record nanti student datang dengar tak dengar, and then ya, sebaiknya datang dengar, okay? Dengar live, secara live. Okay, here is the attendance, yeah, for the QR code. So thank you for attending.